So hello everyone, welcome to our video. Today we are gathered here again to solve this hell of an integral out here. You can see this, here it is, and give it a try before watching the solutions which I'm going to discuss. So we are going to discuss two approaches for this problem. One is a lot more rigorous than the other. So without any delay, let's begin with the solutions. So here is the first solution out here, which was posted by Mr. Safal Das Viswas on my LinkedIn. So it begins by the most intimidating substitution in this problem, which was to substitute t as x square. So after putting this, dt becomes 2x dx, and after some simplifications, I becomes this. And we know that after changing the variables, the value of I doesn't change. So we do that from t to x. Then we have I as this in terms of x. Then comes the most breathtaking part of this video, which was this substitution x square is equal to tan t. Then we have t is equal to arc of tan x square, which is tan inverse x square. Then by using chain rule, we have dt as 2x dx upon 1 plus x power 4. So we get I as this. So we put tan t as sin t by cos t, and we get this. And then we use the property that f of x dx integral from a to b is just equal to f of a plus b minus x dx from a to b, which is also called the King's rule. And after doing this, we get I as this. And since both of them are equal, we simply add them, and then the denominator cancels out with the numerator, and we have just this thing left here, which gives us I as pi by 16, which is our answer. And personally, the best thing about this solution was this substitution. I also started out with this substitution as t as x square, but I could not finish it off successfully as Mr. Safaldas Viswas did. But anyways, let's move on to the second solution. And since I was not able to solve via this method, I had a different route altogether. After some 2 or 3 tries, I got the idea of substituting one thing, which is x is equal to 1 by t. And why exactly did I think of this? I would not like to comment on this. It was just intuitive, I would say. So from this, we have dx as minus 1 by t square dt. So I becomes, in terms of t, as 1 by t cube upon 1 plus 1 by t square into 1 plus 1 by t to the power 8. And we take this minus outside here, and here is the integral 1 by t square dt. And as x varies from 0 to infinity, 1 by t varies from infinity to 0. And with the help of this minus sign, we can just flip over the limits of this integral. So we have I as 0 to infinity, 1 upon t cube. Then we take LCM and take some stuff to the numerator, 1 plus t square into 1 plus t power 8. And we have a numerator t square into t power 8. And we already had this 1 by t square here into dt. Cancel this with this with this, with 5 left remaining. And we again change the variable from t to x, since it will not change the value of our integral. So I becomes integral 0 to infinity x to the power 5 upon 1 plus x square into 1 plus x to the power 8 dx. So let's name this equation 1 and original as 2. So we just add 1 and 2 to get 2i as integral 0 to infinity x cube plus x to the power 5 upon 1 plus x square into 1 plus x to the power 8 into dx. So we take x cube common from here. We have 2I as 0 to infinity x cube into 1 plus x square dx upon 1 plus x square into 1 plus x to the power 8. We cancel these two stuff. So we are now left with 2I is equal to integral of 0 to infinity x cube upon 1 plus x to the power 8 dx. Now this is a pretty standard integral. We can substitute x to the power 4 as cube. So we get 4x cube dx as du. You can multiply a 4 here and a 4 here to get 8. So we have 8I is equal to du upon 1 plus u square. And also the limits remain the same, 0 to infinity, which is simply tan inverse of u from 0 to infinity, which is tan inverse of infinity, which simply converges to pi by 2. And hence we have the answer as I is equal to pi over 16. Yeah, so that was my solution, which was a lot different than how this solution was. But anyways, that's it for the video. Do like, share and subscribe. Thank you.